Um, Good morning, ladies and gentlemen. Oops, excuse me. Anyway, good morning. Today it is our great pleasure to welcome Professor Panos Papanastasiou from University of Cyprus, who that going to share one of his most favorite topic, which is plastic deformation. Panos' name actually very often associated with plasticity. So I'm so glad that today, Panos, you share this with us. Before the meeting, as I mentioned, all of you are actually familiar with as well the rule of those, there is no rule for Robe talks, it's Carol technical talk. But we basically ask you not recording or taking picture or anything. And but over the past, nearly all the presenters are waiting to release their recording. So it's today. So Professor Papanastasiou kindly offering this video recording so that you can catch up. And I will release the link as well as downloads after the presentation, the newsletter. Usually we release newsletter in the weekend, just to pay attention to that. Before the meeting start, I think we need reflect on this safety, this health, that pandemic in this new environment. If you will, how people adapt to this new environment. I have to say it take toll. It take toll regardless you are healthy or not, mentally, physically, not only yourself, but also the people around us as well, family members and kids and grandparents and friends, of course. And that's one of the reasons why we do, that's the main reason we are doing Robe talks, is to keep people connected and entertained, if you will. Stimulated during this pandemic when everybody was quarantined and staying at home. So right now the situation in the US is pretty severe, especially in Houston, Texas. We become most mentioned in the state in the CNN, not for the good part, but the thing is that wearing mask, not anything else, but only for health reason. So everybody wear a mask. For yourself, more for the people around you. That shows the responsibility, shows the person that you care. So we will come out, any pandemic in the history, people come out strong and become stronger. That's where we are. We hope we put behind us this worst period, and with the fun we having in these Robe talks, we come out actually technically and mentally stronger. With that, let me briefly introduce Panos, as many of you familiar with him. And Panos, I have to say, last time when you showed the first next slide, I was thinking, oh man, so 2002 was the year I met you actually, when you were in Cambridge Research Center with John Cook. Very nice settings. We had a very good lunch, and you provided me such a, far-reaching suggestions on plasticity modeling when I was the Eclipse developer for simulations, reservoir simulations. So Panos is a professor now at the Department of Civil and Environmental Engineering at the University of Cyprus. He is actually the founding head of the department and the Dean of Engineering School, and Director of Master in Petroleum Engineering program. Panos, of course, as you know, is graduated from Greece, from Athens, NTU in 1984. And he also is one of the University of Minnesota graduates in geomechanics world. Actually, the Minnesota is like a tag that become it's always be a fashion, if you will. It's actually the credo of the U.S. rock mechanics. He worked many years in industry at Schlumberger, various locations, and that's why he was greeting Colin Sears and all his old friends. And he is currently working on many geomechanics related applications, such as variable stability, hydraulic fracturing, that is one of his favorite, and CO2 storage as well. With that, and I think for the folks who want to ask a question, please type into the chat window. Panos will address them after the presentation. If couldn't address all of them, he will follow up with emails as well. I will have his email address in my newsletter for you to contact him in case you have further questions. With that, I am going to leave the floor to Professor Panos Papanastasiou. Go ahead.
Thank you very much, Gang-Han, for the introduction, and thank you, Andy, also for making available the online infrastructure of your institution. I would like to thank you in particular and congratulate you for organizing this very successful hydraulic fracturing Robe talk series. It is one of the positive things that came out of the coronavirus crisis in our profession. And to say that we learn and use the new tools for teaching online and for organizing exams and meetings very successfully. Within the worries, we had positive things. We had the chance to spend and enjoy more time with families. This crisis is a life experience, as Gang-Han said before, and will come out strong. But I wish to get back to normal very soon and see each other in one of the forthcoming scientific meetings. Until then, all keep safe. Now, as you had seen from my affiliation, I'm based in Cyprus. For those they do not know, Cyprus is the big island in the Eastern Mediterranean. It is an independent country, member of the European Union. The main activities, the economy is based on tourism and services, but there is an ongoing exploration activities in offshore deep water, and we had some discovery of 3 gas fields by the operators. The operators in the area is Noble, Eni Total, and ExxonMobil. Now you will see also in my affiliation, I listed Schlumberger Cambridge Research, and you will see next in the acknowledgement of the support and people I work with them. This is basically, I started working on hydraulic fracturing in Schlumberger Cambridge Research in '91. I had collaboration with people well known in the industry in petroleum geomechanics and hydraulic fracturing. I mentioned first Mark Tirselen. He was a very good man and a great scientist. Unfortunately, he died young 10 years ago. I will always remember and acknowledge the contribution of Mark Tirselen to my work. I worked also with Emmanuel Detourné, Jean Deroche at that time, and later with, sorry, just a moment, please, to find the laser. Okay, I will get. And later I worked with Colin Atkinson on some analytical models, which I will show. At that time, we had a good collaboration with a group of Hans de Pater in Delft University as well. I moved to Cyprus in 2002. I had some support on the hydraulic fracturing from the Cyprus Research Promotion Foundation, and I worked on related problems, smaller problems with people in Greece, Euripides Papamikos, and SINDEF in Norway. Those were smaller projects. And currently, I have funding from European Regional Development Fund and the Republic of Cyprus as some new collaborations here. So I will focus on hydraulic fracturing in weak rocks. And I have the applications and issues here. Of course, the main application is to stimulate oil and gas reservoirs. It can be used to reject in shallow formations, softer formations, but this work is particularly useful in the design of frac packs for sand control. The objective is to predict the pressures for hydraulic fracture in the fracture dimensions and containment. And in hydraulic fracturing shale reservoirs, it will be useful to have a kind of index for interval selections, and I will show one such index within this program. In CO2 geological storage, we can relate this work to the risk of CO2 escape through hydraulic fractures and address also the problems of well ejectivity. We can improve well ejectivity. And there are other related applications. Sciences are common with environmental engineering applications like waste disposals and cleanup of contaminated sites, and in geotechnical engineering, many similarities with injection of grout, and in dam constructions to avoid hydraulic fracturing. So I will, just to keep your interest, I will make some claims like an attorney, and then I will try to prove those just to keep your interest. I will claim that in soft formation, we have high net pressure, shorter and wider fractures. We have high apparent or effective fracture toughness. This effective fracture toughness increases with propagation length, but in short reaches a limit value. This effective fracture toughness is greater when the fracture front propagates in the vertical direction, upward, and hence a fracture will propagate in the horizontal direction, even in the absence of barrier layers. There is issue with the hydraulic fracture closure pattern and the interpretation of the mini-frac and the determination of the closure stress on proband. And the last claim, and brittleness index in hydraulic fracturing must be a combination of the rock strength with the situ stresses. So we started this work to answer the question of the high net pressures. This was a big issue in the oil industry back in the beginning of the 90s, how to explain the high net pressures. And some of the proposition was say that near the fracture tip, there is a fluid lag, Therefore, we need higher pressures back at the wellbore to propagate the fractures. Then there was the addition that the rock dilation will enforce even larger fluid lags. This was not true, actually, as I will show. There is, in the field, we may have higher apparent fracture toughness due to the scale effect, the confining pressures, heterogeneity, and plasticity. Or in the field, we may underestimate the closure stress. And if we underestimate the closure stress, then we will underestimate the propagation pressures. To answer all of these propositions, we set up a finite element model. Actually, it was quite advanced model with modeling of hydraulic fracturing in the fracture, allowing for the formation of fluid lag. And we look at also, the model was able to model plasticity in weak rocks near the fracture tip. Due to high shear stresses, we may have the formation of these plastic zones, as you can hear here. And if these plastic zones are formed, then the energy will dissipate at this energy, and not enough energy will reach the tip to split the rock. So that we will need higher pressure back at the wellbore. One can think also like that these tips, the shape of these plastic zones around the tip shields the tip actually. Therefore, we need higher pressure to propagate the fractures. To answer all this, as I said, we set up an advanced elasto-plastic, fully coupled hydraulic fracturing model. We model the fluid flow in the fracture, assuming Newtonian viscous fluid, lubrication theory. For the rock deformation, we allowed for more Coulomb flow theory of plasticity for yielding. And for fracture propagation to split the rock, we use a very advanced model. I think is the most advanced model for non-linear fracture mechanics, which this model, the cohesive model, simulates the softening behavior of the rock when it is stressed before it splits. And we can simulate that. This was the fracture propagation criterion, but at the same time, I was calculate the path-independent J integral, from which it was possible to calculate the effective fracture toughness during propagation. So the fracture was propagated based on the cohesive model, but the J integral was able to give us the elevated fracture toughness. Finite element analysis, fully coupled solutions, meshing, remeshing to do long propagations. And you can see in the pictures here, the fracture profile is just a quarter of the fracture due to symmetry. It starts from here and it propagates. This is an elastoplastic solution. The fracture profiles as the fracture propagates. And I will show some comparison. With plasticity, we get wider fracture compared to elasticity. And if I go to the pressure profile, we have wider fractures with plasticity. So with plasticity, the fluid front reaches closest to the peak, and we have all the pressure drop near the tip, as you can see here. And back at the wellbore, the pressures are quite close. Next, I will show the net pressure as the fracture propagates, the elasticity and plasticity. What we can see here with plasticity, actually, the net pressure increases at the beginning until the plastic zones are fully developed, and the effective fracture toughness actually is fully developed at that point, and then decreases like the elastic solution. And here we have the effective or apparent toughness, as we call it, as a function of the fracture extension. It starts, increases the effective fracture toughness, but it reaches a kind of a limit value after some propagation steps. With elasticity, of course, the toughness remains constant. Now, how important is plasticity? It depends on the scale of the plastic zones. If the plastic zones are small, plasticity will not be important. So we attempted to scale the plastic zone to see on which parameters will depend on. And of course, the first parameters we found, it's the deviator of the stresses, the difference between the stresses along the propagation direction minus the stress normal to the fracture plate. The closure stress is that, as you can see. It will depend also on the toughness of the material, the tensile strength. This is a question from the classical fracture mechanics. But then from the analytic work we did at that time in Schlumberger Cambridge research and the very famous solution published, we can get this characteristic length, which includes the plate strain modulus and the pumping parameters and the compressive strength of the rope. So overall, we could say we'll get larger plastic zones if we have high elastic modulus, high pumping rates, high original toughness, and low rock strength. Basically, these parameters change the stress concentration near the tip and create larger plastic zones. So, and then I have computational results to show, to make the point. And you can see two examples. In the first example, we have some fixed parameters. And then we look at different cases. In the columns, we vary the rock strength, is the ratio of the compressive strength over the tensile strength in these 1, 2, 3 columns. So the third columns correspond to the weak rock, let's say, the first to the combited rock. And in the rows below, we have the stress field. The first row corresponds to the isotropic stress field. That will be the case when the fracture front propagates horizontally, let's say. The third row corresponds to an isotropic stress field, and that will correspond to the case when the fracture front propagates vertically. In that case, you see from the calculated effective fracture toughness, we have high effective fracture toughness when the fracture propagates vertically, when the fracture propagates vertically compared to the case when the fracture propagates horizontally. In the second example, what we varied, we kept the same rock strength ratio, compressive to tensile, as you can see, and we vary the pumping parameters in the columns, the pumping parameters, and again, different stress field in the rows. Again, you can see here, of course, when we have high pumping rates, we get higher stress concentration and more plasticity, but this effective fracture toughness is particularly high when the stress field is anisotropic. That's the case when the front propagates vertically. And of course, to show you some results, I found these experimental results published in this paper, Funazzo et al. In 2004, which in this paper, they measure the fracture toughness as a function of the confining pressure. And you can see here the big increase in the fracture toughness as a function of the confining pressure. Under zero confining, of course, it's here, and the under confining pressure are now 9 megapascal. They had an increase in the fracture toughness by 5 times. And you can see that the diagram shows that it will still increases for higher confining pressures. And of course, we know that we do hydraulic fracturing under confining pressures, confining pressures. So that justifies the elevated effective fracture toughness that we found. Now I will look at the fracture closure. So again, with the plasticity solution, we propagated the fracture, and it reached that fracture profile, which I show here. You can see the last line. And then I will allow the fracture to close down. And this is the fracture profile. As the fracture closes, you can see that it closes quite a lot. Almost it covers the closures the half of the volume without changing the fracture length. And then the fracture closes like in a zip pattern, It closes first near the tip, and then the closure lasts near the wellbone. In the diagram here, I have the net pressure actually during propagation, which was like that, and then allow the fracture to close after it had reached 5 meters, like that. And I propagated the log, and I allow the fracture to close after it had reached 8 meters. Again, you see a great pressure drop when we stop pumping without changing the fracture length. And then the pressure drops and the fracture closes completely at negative net pressures. So if we interpret the closure stress from this point, we'll underestimate the net pressure. We will underestimate it. At that time, Schlumberger and other companies that were supporting the hydraulic fracturing consortium in Delft University, and they ran some tests there, the group of Hans de Bader. You just see a schematic of the test on large blocks, on strong rocks and weak rocks, strong rocks from cement, weak from plasters. And they had these systems with all the kind of monitoring devices, acoustic transducers, pressure transducer. So they monitor the fracture as it was propagating and closed. And I will show some of the results. Actually, yes, this is some of the results for the net pressure as the fracture propagates. And for the fracture width, as the fracture propagates, the net pressures are quite close. And even for soft blocks, it's lower. And the reason, as I show in the results, when the fracture is wider, the fluid front reaches closer to the tip, and back at the wellbone could be very close or even lower as it shows here. But here you can see clearly that it's much wider, the fractures in the soft blocks. Now we need to be careful here, because we need to compare the results for the same pumping time. And if you compare the results for the same pumping time, we will find that with plasticity, the net pressures are higher for the same pumping time. And now we will look at the closure in this experiment in stroke rock, let's say, the strong plaster, and weak rock, weak plaster. In the case of the strong rock, you will see that when the pressure in the fracture drops near the confining stress on the block, the fracture had closed. You can see here in the red line that the fracture had closed. We are quite close. Now, if we go to the weak rock or weak plaster, you can see that when the pressure drops to the value of the confining stress, which is around here, the fracture is still open, widely open. And actually, it will close the fracture here at negative net pressure, at pressures lower than the confining stress. So again, we need to be very careful with interpretation of the mini-flat in weak formations. The other thing which I forgot to mention, so if I allow me to go back a little bit here, when the fracture closes first near the tip, the proband near the tip will be under higher stress, and then it is a matter of equilibrium. The proband back at the wellbore will be under lower stress. So we need to be very careful with the closure stress on the proband. So, and this is one of the pictures actually from the Delft consortium, which show the fracture roughness in the weak plaster. And you can see in this case, in the area where the fracture was propagated, in the wet area and in the dry area, the fluid front is here, the fracture tip here. You can see how rough is the surface probable due to plasticity. Now, one of the applications that we wanted to do hydraulic fracturing in weak rocks, it's for sound control. It's for sound control. And basically, the idea is that if we do hydraulic fracturing and then allow the fracture to close on the proba, we redistribute the stresses. And with the stress redistribution, we decrease the shear stress. And this is what we see here. This is the stresses here before fracturing, far away ahead of the tip. It's like before fracturing. And then after we fracture, we are here, the stresses are here, and you see they became closer. And then this can be seen clearly in this diagram here, so which shows this, how close we are to the failure. Let's say that the failure line, which is defined by the rock strength, is the red line, and the blue line, it's the stress concentration, according to the Moore Coulomb, let's say. Now you can see, before fracturing, the stress state is very close to failure. Now, if we do hydraulic fracturing and allow the fracture to close on the proba, we push the stresses away from failure. So here, basically, we are just on the fracture surface. You can see that the stresses move away, far away from the failure line. And this is as we move to the distance perpendicular to the fracture surface, to the fracture surface. So far away, it's like not seeing the hydraulic fracture. But very close to the fracture, we push the formation away from failure. We extended this work by looking into the role of the pore pressure and the leak-off in the formation as well. And so we look at also some of the sensitivity of the results on the fracture criteria of the cohesive model. And just to say for people that they do such modeling, the shape of the softening of this curve, it's not very important if it is linear or exponential. What is important, it's the area under the curve, which is equal with the strain energy release rate. We found also that the initial slope, the stiffness, will be important in hydraulic fracture. And some of the results with Poroelastoplasticity, the solid line, the fractures are wider from the poroelasticity and the pure elasticity. The same tendency with the net pressures with poroelastoplasticity are higher compared to poroelasticity and elasticity. And of course, now we may have some practitioners here, and they may say, it's difficult to do, of course, finite element with plasticity. The problem is highly nonlinear, fully coupled. For the design purposes, it's quite difficult. And then practitioner will say, what I can do to get my results closer to the results of plasticity. What I will advise for the practitioners is to use the unloading elastic modulus in the classical hydraulic fracture simulators. The reason of using the unloading elastic modulus is because near the fracture tip we have plasticity, but once the fracture propagates, behind unloads elastically. So the bulk of the area is under unloading mode. So to use the unloading elastic modulus, which is very close to dynamic modulus and actually quite easily available in the industry, petroleum industry, and to take care of plasticity with effective fracture toughness. So to show that, I have one of the diagrams which shows the calculation of the effective fracture toughness with fracture length. So I will take the limit value here, and I will use this limit value in the elastic simulator, and then to compare the results with the full plasticity model. And this is what we did here in this diagram. The initial fracture toughness before propagation, the elastic fracture toughness, I will say, was 2. And this was the prediction by the elastic model. If we use the effective fracture toughness, the limit value, the pressure profile is this one here, as you can see. No, actually, this is not the fracture profile. This is the fracture opening. Okay, this is the fracture opening. So this is with elasticity with effective fracture toughness, and with full plasticity. You can see here that the effective fracture toughness prediction is close to elasticity, and the same results we can get with the pressure profiles. The pressure profile predicted by the effective fracture toughness is quite close to plasticity. And I have another example where the effective fracture toughness in this time actually was 34. It was for much weaker material. So we got effective fracture toughness 34 megapascal square meter. And then we use this elevated in the elastic modulus. I will say now, and at the top we have the pressure profiles in the fracture, which is quite close again to plasticity. And in the lower, we have the fracture profiles, In this case here, we don't have a good matching as before. It's narrower, the plasticity near the tip. The reason is because the the model we used was full dilatat. Full dilatat means that the dilation angle in the plasticity model was equal with the friction angle. It was full dilatat. In reality, actually, the dilation, it's lower than the friction angle. So if we have plasticity with dilation lower than friction angle, non-associative plasticity as we call it, I believe the result will be closer. And we tried with some analytic work to look at also the influence of the dilation of non-associativity. And we found that the non-associativity solution is between the elastic solution and the solution we get for associative solids, for associative. So the non-associative is in between. One of the things we found with non-associativity is that it gives a kind of a boundary layer in the stress concentration near the fracture tip. And more recently, we did some calculation looking into the influence of the shear stress from the viscous fluid, of the shear stress loading from the viscous fluid. And again, we found the difference it makes is in the emergence of these boundary layers in the stress concentration near the fracture tip. But I will not spoil it further. Let's go to more obvious things. And it's nice to have analytical models because in the analytical models, you can identify critical parameters. And we tried to develop an analytical model to take into account plasticity. And at that time with Professor Atkinson, he retired from Imperial College now, he was always consultant for Schlumberger. We developed this model based on the dislocation theory. And with this model, we replace the distributed plasticity, you can see here, with super dislocations that are sitting in the center of the gravity. And of course, we had different conditions to satisfy in order to determine the location and the strength of the dislocation. Conditions to satisfy was the stress intensity factor at the crack tip to be equal with the toughness for propagating, at the dislocation to satisfy the more Coulomb yield criterion, and also that the crack act to maximize the crack opening displacement. So with this analytical model, in some particular cases, like small scale yielding, when the plastic zones are much smaller than the fracture length and the fracture toughness is 0, it's possible to derive the equations in dimensionless form, as you can see here, for the length of the dislocation, the crack opening displacement, which is the strength of the dislocation, is delta actually. B is the strength of the dislocation, delta is the crack opening displacement, and there is the force, which is a good measure of energy to propagate a fracture. And here with this function, we can identify some critical parameters, which you will see more clearly in the results I will show next. So the first critical parameter actually, it's the parameter you see here in the horizontal axis, the difference between the stresses along the fracture propagation minus the closure stress divided by the undrained cohesion of the material. So this is for frictionless or undrained analysis, let's say. And these are the parameters which I shown before, calculate all in this diagram. And we have the solid lines for small scale yielding and the dashed line for large scale yielding. When the fracture propagates in the horizontal direction, the stresses are close, so we are in this area here. We can induce the fracture, it propagates easily. If we are in highly stress anisotropy, we are around this area here, which is more difficult to propagate the fracture. We need increasing energy to propagate and induce a fracture. Similar results for the case of the cohesive frictional material. Now the critical parameter, it's a combination of the stress field as before and the rock strength. Now we have the cohesion, we have also the friction, but this is the critical parameter. Again, the case when the front propagates horizontally, it's here, easily to propagate the fracture and to induce fracture. And when we move to this here, for propagation in the vertical direction, more energy, you see, increases dramatically to induce and propagate a fracture. And based on these results, actually, it's we thought about to propose a new brittleness index or parameter, and there are many definitions actually in the literature. This is from a paper published by Runehor in 2015 with different definitions. Some of the definitions are based on the stress-strain curve, some of the dynamic measurements. And of course, we need to be very clear, some of these definitions do not follow the expected trend, the formation to be more ductile under confining stress. So based on the results I showed before, we propose a new parameter which can be used as a brittleness index, which is a combination of the stresses and the rock strength and the rock strength. In this, we have the cohesion and the friction. This is a new definition. And some of the applications which I mentioned before to look at in the risk of inducing hydraulic fractures during CO2 injections. So what basically I had shown is that it's more likely that the fracture will propagate horizontally, even in the absence of a stress barrier on the top and below. It's more likely that it will propagate horizontally than vertically, so it's less risky. And if the fracture propagates horizontally, will have some positive effects. It will solve the wellbore ejectivity problems, which is a problem with CO2 injection. And also, if the fracture propagates long, it will increase the storage capacity of the formations. And the other thing we did, of course, the CO2 injection due to the corrosive nature may change the material parameters. So we tried to make a comparison using the analytical model which I showed before to compare the results when we have the risk of fracturing in the virgin material and in the case when the rock strength was severely damaged due to the corrosive action of the CO2 injection. And in that case, actually, we decrease the rock strength, like the tensile strength and the rock strength and the fracture toughness, the original fracture toughness, by 10 times. And then if we look at the results the solid lines here are for the virgin material, and the dashed lines are for the corrosive material. You can see here that even in the case of the corrosive materials, it's more difficult to induce hydraulic fractures. It's more difficult to induce hydraulic fractures in the case of the corrosive material. This is the prediction of the model. Actually, what it will trigger more plasticity because the rock will be weaker, and then it will shield the tip, and it will not be possible to induce hydraulic fracture. Of course, there are other risks for the CO2 escape, which we'll not address in this point here. But at least we see that, again, this is for frictionless, this is for frictional material, for fully frictional material. Even when we have the severe damaged material due to CO2 injection, it will be more difficult for the CO2 to induce hydraulic fractures and the CO2 to escape. Now, I make many times the point that it's very likely for the fracture to propagate in the horizontal direction rather in the vertical. Of course, someone may say, but look, if we propagate vertically, then the closure stress decreases. So it will be easier for the fracture to propagate vertically as the closure stress decreases. Then I tried to do some comparisons here. So I started with definition of the net pressures, which the pressure in the fluid minus the closure stress. And for the linear elastic fracture mechanics, the stress intensity factor is the net pressure times the square root P times the half length of the fracture. We can write it like that, within replacing the net pressures, and the fracture will propagate when we reach the fracture toughness. So then I can solve for the pressure in the fracture, which is the closure stress plus the toughness divided by the square root of P times half of the fracture length. So this is the equation now. Now, we know that the local stress gradient for the horizontal stress, it's around 50.8 kilopascal square meter or 0.7 psi per foot. So if the fracture propagates vertically upward, the resistance will decrease by 15.8 kilopascal per meter. But we will have the increase of the fracture toughness, and these results, which I showed before, show elevated fracture toughness of the order of 10 megapascal. I show you results of before around 35 megapascal times square meter. And actually it doesn't need long propagation for the fracture to reach this value of the fracture toughness. So apparently here we're talking about megapascal, here is kilopascal. Of course, we need to take into account the length of the fracture, but as I say, for it reaches the asymptotic value for very short propagation. So the conclusion is the fracture will propagate horizontal. Actually, now, if the fracture propagates horizontally, the closure stress doesn't change, and the resistance, the effective fracture toughness is smaller, as we say, smaller. So it's very likely that the fracture will prefer to propagate horizontally. Now, if I see the time, we are getting close to the time. Actually, the conclusions, I mentioned this many times. The role of plasticity as a shielding mechanism, increases the effective fracture toughness. In short, it reaches limit value, depend on the propagation direction relative to the stresses. What else we show? higher net pressure, wider fractures with plasticity. We need careful interpretation of the mini-frac to obtain the closure stress. We have good distribution of the stresses near the fracture tip and push away the formation from failure. The definition of the brittleness index, which is a combination, as I say, of the stress field and rope strength. And I mentioned also the relative application CO2 injection for estimate the risk of CO2 escape through hydraulic fractures. I will close here, and as I say, the presentation will be available, and I will try also to answer questions. Thank you very much for listening to my presentation. Let me try to see the chart, how to find the...
Yeah, thanks, Panos. While you were looking for the chat window and find the answers, I just like to see that this is fantastic. I have to see 20 years ago, you enlightened me in this plasticity world. And today you did that again with this fantastic presentation on hydraulic fracturing. This is not only in depth, but also the coverage as well. Thanks for sharing this.
Thank you very much. I hope I try to make it clear. I hope I managed to do it. Thank you.
You actually, the plasticity itself, as you know, much better than anybody else. It's such a complex problem, but you always explain it in such a clear way that for the folks that can understand. And before Panos answers the questions, I would like to announce the next Robe talks next week. Okay, well, first of all, we have 2 more Robe talks before we wrap up this series. As I mentioned in the email newsletter, the Robe series has been tremendously helpful and successful, thanks to all the speakers and the participants too. But every good party has ends. It doesn't mean the fun stops. We have multiple events coming that actually with excellent technical contents to entertain and engage the technical communities. But next week we have Thomas Finkerbell from Keft in Saudi Arabia that's going to share his experience and studies in the in-situ stress. So that for the folks not familiar with, but the Keft is one of the prestigious technical research institute in Saudi Arabia, and you will hear more from Thomas next week. But in all the time, Panos, feel free to take over to answer some of the questions. You probably just a couple of them, and we follow up with the rest through the emails.
Yeah. Okay. Yes, I will try to answer as much as possible, and if we don't manage with the time, then I can send you my written answer. Let's start with a question. The first comment, it was about the presenter screen. I hope it wasn't any problem during my presentation. It's too late now anyway. I hope it was okay. The next question by Surej. Hi, Panos, thanks for excellent presentation. What do you mean unloading? If that during the actual test phase, on my experience, it can be higher. Is that you propose? What I said is to use the unloading modulus. Actually, the unloading modulus is quite close to the dynamic modulus, especially for small amplitudes, as we had seen. And as the as the large formation, it's under unloading, this is what I propose. Of course, if it is smaller than dynamic modulus, this is the role of plasticity as well, and we will take into account the plasticity with effective fracture toughness, which will introduce in the model. In any way, let's put it that way, and dynamic modulus is the upper bound of the unloading modulus. I hope I'm clear. The second by Makti Haddad, to everyone, consider that the common fracture toughness measurement for the reservoir rocks using scratch test gives values 1.7 megapascal square meter. Will you please explain the condition to obtain 35 megapascal and 20 times more? And this is what we calculated. Huh? When you measure in the scratch test, it's not under confining or under plasticity condition. To the contrary, I had shown the results of one of the papers which had shown increase of the fracture toughness by 5 times and was still increasing at higher pressures. In this model which I presented, I didn't impose anything. If the material, if the rock was very strong, we will not get any increase in the fracture toughness. But if the material was weak, this is what we got in the calculations. Did you perform a sensitivity study on the dilation angle? How important is it in modify P-net and fracture width? Actually, as I say, the less dilatant material, it's between the elastic and dilatant. So dilation, it may, lower dilation will get slightly narrower fracture, but plasticity, it will still be there. Huh? So we need to separate dilation from plasticity, of course, okay? We can have full plasticity with less dilatant material as for rock. As I say, what we know now is for less dilation, we are between elasticity and the full dilation model. From my friend Eddie Shepard, it's a long time to see him. Makti, you can measure toughness at confined stress in rock lab. There are a number of papers published. Very nice, yes. I show one of those, yes. From Fushen Liu, in your experience, how large the plastic dissipation may be in terms of the energy budget compared with elastic potential energy, fracture, surface energy, fluid viscous, dissipation, so on. As this is what I show, the measure for me of the energy dissipation was the effective fracture toughness, the elevated fracture toughness, which I calculated. This is the measure of the dissipation of the energy. From Tom Bratton, ex-colleague, Schlumberger, how might the analysis be different if the background formation is itself in a post-yield state? Tom Bratton means that the post-yield state, what that means, post-yield state, what I can think is that the formation is very close to plastic yielding. To move away, of course, even if it is in a post-yield state, the fracturing will bring it again to the yield state. So I hope I'm clear. From Chenko Lee, Panos greetings from Minnesota Mafia, and the compliment, huh? I have the compliment here. Thanks for the excellent talk. As usual, I enjoy your plasticity. Can we understand strange softening behavior in horizontal and vertical sample rock, respectively? as a replacement of the horizontal and vertical frag. It's not a matter of sample or rock orientation, but orientation with respect to the in situ stresses. Yes, you can investigate that with the applied in situ, different in situ stresses, definitely. This is what we can do. So these are the comments. I don't see any other comment.
Excellent. I'm sure if folks still have questions, Panos' email will be in my newsletter, and feel free to send Panos your additional comments or compliments, especially compliments to Panos. And thank again, Panos. This is great. This is fantastic. Thank you for teaching us again. And for all the rest of folks, stay well and healthy. That's the most important thing we are doing. And we will see you next week. Take care and have a safe moment. Okay. All right. See you next week, Panos. Thank you very much.
Thank you very much. Thank you, everybody. And I hope to see you soon.
Yes. I look forward.
Okay.